Now we're back to Lewis structures, and this time we're going to talk about formal charges associated with Lewis structures. You see, Lewis charge is up here, okay, blocked by my giant head. So Lewis structures, formal charges, and I've got a structure drawn up here, okay, and this one is this molecular formula. This one is C2H, 1, 2, 3, 4, 5, 6, 7, N. All right, that's what this structure is. And what we have to do is whenever we're approached with any type of Lewis structure, we have to look at it and decide if there's going to be charges associated with things, okay? Now there's some tricks and shortcuts I'm going to show you how to get there after I discuss the formal way of doing this, okay? When I look at this, and the particular ethylamine is the structure that I've got drawn up here. And we want to determine what the actual charge on each atom is on the molecule. The first thing that you have to do is look at things that have one bond. Halogens and hydrogens. Okay, and I've got nothing but hydrogens drawn up here. And what is the formal charge? To calculate a formal charge, what I do is I use the valence electrons. So normal valence electrons, okay, NVE, normal valence electrons of the structure. Okay, and then I subtract 1 electron per bond, and I subtract 2 electrons per lone pair. All right, and what this is going to end up giving me is the formal charge of that particular atom in the Lewis structure that I have drawn. Okay, so let's start off first, and I'm going to prove to you that you don't have to worry about hydrogens as far as charge goes. Okay, so I'm making a lot of noises that you never wanted to hear come out of my mouth today. So let's look at this hydrogen that's up here. Okay, hydrogen, this guy. How many normal valence electrons does hydrogen have? Okay, and as far as normal valence electrons, hydrogen, it's got 1. So NVE is going to be 1 here, okay? And we're going to lose 1 electron per bond. The hydrogen has 1 bond to carbon, so I subtract 1, okay? And minus 2 per lone pair, okay? And it doesn't have any lone pairs, so that's a 0. So 1 minus 1 minus 0, the charge there is 0. And for any hydrogen that's got 1 bond, the charge is always going to be 0. So 0 for every hydrogen that we've got. And you're never going to see hydrogens with actual charges because that would mean they've got something weird going on with their bond. That just doesn't really happen in normal molecules. So all of these have 0 charges. So first and last time you ever have to worry about labeling the charges on any hydrogen. 1 bond, no charge. Okay? However, for carbons, oxygens, nitrogens, phosphorus, sulfur, anything that's got more than 1 bond, that includes halogens with more than 1 bond, you'll have to worry about the formal charges associated with them. Okay, so let's look at these carbons. And what I'm going to do is I'm going to identify this carbon here, right? And we are going to calculate the formal charge for that one. NVE, how many normal valence electrons does carbon have? It's got 4 Lewis dots, so it's going to have 4 normal valence electrons. So 4 electrons there, okay? How many single bonds does this one have? 1, 2, 3, 4. 4 electrons, okay, so we can subtract 4. Lone pairs are 0, so that's a 0. Anytime you have a carbon that's got 4 bonds to it, it's not going to have a charge. Okay? There's a pattern developing here, okay? So if it's got 4 bonds, it doesn't have a charge. So this carbon is 0. What about that carbon? Does it have 4 bonds to it? 1, 2, 3, 4. No lone pairs. So the charge on that one is 0 as well. The nitrogen that's there, okay, this one's got a lone pair. So I have to worry about that one. So for nitrogen, the NVE is 5 for nitrogen. Okay, I've got 3 bonds, so I subtract 3. Now I'm going to subtract 2 for the lone pair. And that's a 0. Okay, everything in this case is zeros. So what does that mean the overall charge of the molecule is? Well, in this case, you're just going to take all of the charges that are there, add them up. So you add positive charges, subtract negative charges, and that's you're going to end up with the total charge in the molecule. Well, if I add up all the zeros here, your overall charge is going to be 0. Okay? And if the charge is 0, normally we don't identify a little box up here as the 0 to indicate molecular charge. We just say it's neutral. Okay? We only use those boxes if it does have an actual charge. Okay. And when is it going to have an actual charge? Well, I'm glad you asked, and I'm glad you're talking to your computer screen, because that is how we learn, people. All right, I'm going to change the nitrogen here. Change this nitrogen, and what I'm going to do is I'm going to take this lone pair, okay, and I'm going to put a hydrogen on it. Right, not right. How can you do that? Well, if there's an H plus out there, the nitrogen go out and grab that. Okay, is it legal to do that? Lewis structures. Let's look at it. Okay, does this thing have 8 electrons? Yes. Okay, does the hydrogen have 2 electrons? Yeah. So guess what? This is a legal structure. This can happen. Okay, happens all the time, as a matter of fact. So normal valence electrons for nitrogen. What is it? I just erased 5. That's right. Yeah. I erased it to throw you off. So 5. Okay. Now in this case, I've got 4 bonds here, minus 4, and my lone pair disappeared in order to make that bond. Now in this case, I've got 5 minus 4. My overall result is a +1, so my overall charge for ethylamine at this point, because it's been protonated, it's got a +1 charge. Okay? So the formal charge on this nitrogen is +1. Okay, which means that the overall charge in the molecule itself is going to be +1. Okay? All right. So let me put up a molecule. I'll make it magically appear. And what I want you to do is, once you see that molecule, I want you to pause this and stop. And I want you to go ahead and try to calculate the formal charge. Remember with the nitrogen before, it had 3 bonds because it had 3 dots. Remember the Lewis structure? So the number 3, if it's got single dots, that's the number of bonds you can make. If it has the same number of bonds as the 3 dots, it's going to be neutral. Okay? In this case, it didn't. Okay? It had more, which means it's not neutral. So I'm going to drop a weird molecule, may or may not exist in real life, but what I want you to do is I want you to calculate the formal charges that are associated with everything. All right, voila, here is the weird molecule. Now what I want you to do is I want you to identify the formal charges on everything. Copy it down. If it doesn't have a formal charge, just write a little 0 next to the atom. Okay? And then we'll write in everything else that's associated with this thing. All right? Okay. Now, hopefully, we've got what you have written here. We're going to look at this and try to figure out what the charges are. So the first thing we're going to do is use our shortcuts. We know that all hydrogens, if they've got 1 bond, are going to have a charge. Okay? I'm not even going to write zeros on them. What about the carbons? Remember, carbon, if it's got 4 bonds, it's going to be neutral. So what carbons here have 4 bonds? Okay? So these ones are kind of strange. I'm going to ignore these. But this one, 1, 2, 3, 4, that's neutral. This one, 1, 2, 3, 4, okay, 0. Now you look at this and say, well, Dr. Wayne, you gave us double bonds. We don't know what to do with double bonds. I've been drinking for the past half hour. Not alcohol because I'm underage, right? Okay? We look at this. This bond, okay, 1, 2, 3, and 4. Is there a big difference there? Yeah. Even though it's a double bond, we still count it for formal charge as a bond. So this guy's a 0, and as a result, that guy's a 0 as well. And this one, again, a 0. So all of our carbons are carrying 0 formal charge. Okay? Now, let's look at the other atoms. Okay, let's look at that oxygen down there. Oxygen, right? Oxygen, normal valence electrons is 6. NVE is 6. How many bonds are attached to it? I subtract 3. 1, 2, 3. 3 bonds, subtract 3 for bonds. You can write this on a test or a quiz or anything like that. That's fine. By all means, write things down. I can't give you partial credit if you don't write things down. So write it down. Minus 3 for bonds, and I've got 2 for lone pairs. So as a result, my overall charge on this thing is a +1. for that oxygen. All right? What about those two oxygens that are up top? All right? How many dots does oxygen normally have? It's got 2. Okay? So, got 2 bonds for each. Is that going to be neutral? Yes, it is. So both of these are going to be neutral. So 0 and 0. If you doubt me, do the calculation. Normal valence electrons is 6, minus 2 for bonds, minus 4 for lone pairs. 6 minus 6 is 0. Wow! All right, now that's sulfur. Now you look at the sulfur and you're going to go, hey, it's got what? Bonds, Dr. Ruane? Yes. I've done something evil, and what I've done is I've now violated that octet rule that everybody has written and posted a big poster on the wall. Octet rule, never violate it. If you do, you'll be struck down by God. But I just violated it. No lightning. It's a clear day outside. What have I done? Okay. Remember, sulfur is a 3rd row element. This is the octet guideline at this point. Things can be violated. So I've got sulfur here. Okay. The normal valence electrons for sulfur, I'll put this over here, NVE is 6. All right, and how many bonds does it have? 1, 2, 3, 4, 5, 6. Does it have any lone pairs? No. What's the charge on it? 0. It's a legal structure that's got more than 8 electrons. That's what we call a hypervalent sulfur, and it works. Okay, so there we go. So this is a 0 as well. So what's the overall charge in this molecule here? That's right, +1. Okay? Remember, if something has a charge on it, I like putting a circle around it just to identify it as a charge and don't look at it as an extraneous mark. Okay? Now, I'm going to talk about resonance because it's fun. What's resonance, Dr. Ruane? Well, let me erase the board and I'll tell you. All right. Behold azide. Okay? If you're smart and you're clever, you heard me say azide. We use IDE at things to represent there's a charge. Okay? So azide itself is a charged molecule. So here's azide, all right? And we want to do formal charge calculations on this thing first. So let's do that. Formal charge calculations, all right? This nitrogen, normal valence electrons is 5. Okay? And I've got 2 bonds, and I've got 4 lone pairs. So this nitrogen is a -1. This guy is a +1, and this guy over here, yeah, you guessed it, if I write it correctly, is a -1. So our overall charges are -1, +1, -1. So the overall charge on azide is going to be -1. Okay? Now, whenever I have double bonds and I've got lone pairs, things can go into resonance. Okay? So in this case, with the nitrogen, the electrons can move. And what that means is that I can push electrons out if there's a way for me to push electrons out. So I'm going to form a double bond, or another bond, using those 2 electrons. 2 electrons make a bond. I'm going to make another bond between these nitrogens. Okay? Nitrogen can only have 8 electrons, so if I push electrons in, electrons need to be pushed out. So I'm going to move those electrons there. Now what I get is a nitrogen, okay, with a triple bond between those nitrogens, and a nitrogen over here that now has 3 electrons, okay? These electrons down here, they used to be that bond, okay? This top bond used to be the lone pair that was up there. If I figure out formal charge here, do this in pink. This one's a 0, this one is still a +1, and this one over here is now -2. Overall charge on this molecule is a -1. Okay? Now for resonance, okay, we can't break actual bonds to separate atoms, which means that there's got to be at least 1 bond there. Okay? But we can move electrons around and move the charges. Okay? The overall molecular charge has to remain the same. Okay? We can't lose electrons into the ether as well. So resonance, all it allows is a movement of electrons between various atoms.